Hi, my name is Dan, and this video is one in a short series of videos that I'm doing about the basics of understanding memory circuits in digital electronics, which form part of digital computing, and it's part of, so this series is part of a wider series that I'm doing, which is to go from the basics of fundamental logic gates and to build up a 4-bit simple CPU uh, through this process. So it's quite a long process that we're going through. This particular uh, playlist, short set, is about memory cells, and we'll discuss why memory is important in computers, but also how to achieve it. A roadmap of where I'm going in a wider context is in the description down below. And also there is a link down below to where you can get hold of this software that I'm using called DigitalWorks, which is a digital simulation software. So rather than actually doing this in hardware, it's easier and cheaper to show it in this software. And I encourage you to work along with me and to get a copy of the software and actually to make the things that I'm making. We're building up a part center, some macros that we've made, and we will be expanding that with this series. So, memory. The point of this is that so far in the circuits that we've been doing, any kind of signal that we have, or any state on any wire, is transient, which means that as soon as we change the inputs, the outputs change. And that's good and fine for certain situations. But if we want to get into calculating more complex things than just the simple adder that we've done, we're going to need to be able to remember the results from previous calculations. If we're going to be have anything that's programmable, we're going to need to be able to have a way of storing instructions and remembering things. So digital memory is one of the huge fundamentals in terms of electronics for computing. And so this series shows you how to achieve that in digital electronics. All this stuff is uh, fairly standard and generic in this sequence of videos. And I'm going to start with the most basic circuits, which will be able to remember something. And it's a bit of an odd circuit, so let's plow into it. What I'm going to do is I'm going to create the circuit, and then I'm going to show you it in action. Hopefully, then you will understand what it is and what it can do, and why this is an important thing. I will be turning this into a macro, but in order to demonstrate it, first of all, I'm going to create a circuit which has got inputs and outputs, and this particular circuit has got 2 inputs and 2 outputs. So I'm going to create those, and I'm kind of lining these up as I know they're going to be lined up. So what I've done is I've put in 2 NOR gates, and these are one of the beauties of this is that actually the fundamental thing that we've got is just 2 gates. Here comes the odd bit, is that as well as connecting these outputs to the outputs, there is going to be some interaction between these two. And this is called feedback. So I'm feeding back the output from the bottom half to one of the inputs on the top half, and vice versa. Okay. Sometimes these are drawn with kind of using angled lines. So if you see versions of this circuit with lines that kind of at angles like that, then that's quite common. I've just had to turn them around. So it's a symmetrical circuit in that you've got an input at the top, an output at the top, an input at the bottom, and an output at the bottom. There's 2 NOR gates, and the output from each is fed back to one of the inputs of the other. So that's one feedback, and that's the other feedback. And let's run simulate and show what happens. So this is giving us already an output of 1 at the upper output and 0 at the lower output. And let's use one of the inputs and see what happens. So if I hit that input, it switches these two outputs, so that becomes low and that becomes high. When I stop having that input, then it stays as it was. If I do that again, it doesn't change. Let's use the other one. If I do that, it switches it the other way around. And again, it doesn't matter how many times I do that. So what's happening here is that, although it kind of crosses over, is that this circuit is actually remembering what's happened in previous states. If I hit this again, it'll switch it across. Right, now let's see if I can explain why and how that happens. So if this next passage of me talking and explaining doesn't click and make sense to you, don't worry too much. You then just need to be in a situation where you trust that this works rather than understand why it works. And it does work. And it's one of the fundamental basics of computing is this. So we can see dark lines for when a line is high, grey lines for when a line is low. And at the moment, both of our inputs are low. Here we go. And but one of the crossover lines is high. So a NOR gate, when you have two low inputs, will give you a high output. And in this state where we've got nothing that's high on the input, there are two states that the circuit can be in. It can be either in this state where the lower output is high, or it can be the opposite state where the upper output is high. And I'm just going to demonstrate that by flicking that on. That's the wrong one to change that and then turning it off. So we're back to where we were, in that the two inputs are both low, but the outputs have changed. And what it's doing is it's remembering stuff from earlier. And I was talking about the feedback loop. So now it's changed so that this, because this output's low, this feedback's low, that's also low, so that makes that high. But then if you follow the full circle through, that feedback's high, it comes through to this NOR gate, and because that's high, the output from here is low. Okay. That crossover and the crossover feedback is, as I said before, a little hard to get your head around. So if you don't, then don't worry too much about it. Trust that it works. And normally this would be labeled, it can be upside down or the other way up because it's symmetrical, but we would label this as R and this as S, and this as Q. I don't know why Q is used traditionally for this output, and this as not Q, and the way to do that with an annotation is to use an overbar. They're a little bit small. So for some reason I've got A there. Let's change that to S. Make it a little bit bigger, it's not that important. So these are labeled as S and R. S stands for set and R stands for reset. So to set, we send a pulse in here, and I control that pulse like that. And it sets Q to high, and not Q is always going to be the opposite. It's going to be low. To reset is when we're going to set Q to low. And generally, we become interested in one output rather than having both outputs. Both outputs are available, but we tend to use as a data store this, set it to high using S and set it to low using R. So that gives us a low at Q. If we do it again, nothing changes. If we do it as S, it changes back so that Q is high. Okay, so this is this particular circuit is called an SR latch. A latch means that it will switch to one way or the other way, and it's bistable. Now, there's something that I haven't shown with this at any point. I've been careful not to, which is I've only ever had one of S and R high, And there is an issue with this particular circuit, that if you put both S and R high, then this becomes in what's called an indeterminate state. It's actually 0 there and 0 there. So it's not kind of working properly, or else we want it. So in order to make the SR latch work properly, you should only have one of the two inputs high at any point in time. And as we go into further versions of this is called a bistable, because there are two stable positions that it can be in, states that it can be in. And we'll see a series of variations on this, all of which are useful in their own right. So what we're going to do now is we're going to accept that we've got our SR latch, and we're going to turn this into a macro so that we can use it in the future. So this needs me to get rid of the inputs and outputs and replace them with tags. If you don't know how to make macros in Digital Works, then you're going to need to go and find out, because I'm not telling you in this video, but I do have another video in which I have outlined how to do this. So you could go find that one if you wanted. And that's basically me talking whilst I'm doing this wiring and trying to do two things at once, which can often be a dangerous thing. This is when I make mistakes. This is when I'm trying to talk about one thing and do something different. Here we go. I think that that's correct. So let's open up the template editor, and we've still got our template for the 4-bit adder, which was the last thing that I did. I'm going to basically, am I just going to wipe everything? Oh, might as well. This is going to be a smaller box for an SR latch, and we're going to have inputs at the top of SNR and bottom of Q and not Q. We're going to have some annotations in here as well for our basic SR latch. Bear with me, please. Right, SR latch. Need to make the box a bit bigger because that text is starting to take over. Being tidying things up. And let's call that one S. Call that one R. Call that one Q. And finally, that's going to be not Q. How does that look? Not too bad. Let's do a little bit tidying up if we can. If you've been following these videos through, you'll have noticed that I'm a bit more obsessive about making things neat when it comes to the templates than I am actually the circuitry beneath it, because the templates are the things that then get reused in other circuits. It'll do, it's not quite right, but there we go. So let's do the connecting through of these tags with the pins. Which way around was it? And I've just selected the top one, so that's R. I should have left the annotations in before, shouldn't I? So I'm now doing this from memory. The bottom one's S. Come on. It's very precise. I'm not quite there. There we go. And then the top one was Q. And the bottom one is not Q. So normally at this point I would create another circuit to demonstrate that it works. And even though I have just demonstrated this, I will go through that process just as a matter of good practice. So I'm going to save this as, we're going to call it a SR Latch. And I wonder if I highlight that, can I? I'm going to change that name, so I'm going to delete that and do another save as. Um, File save as, because I'm going to collect together all bistables by using that at the start. So bistable SR Latch, right. New circuits. Where's my bistable SR Latch? There we go. Let's stick on the inputs and the outputs. Two inputs and two outputs. Well, them up. La 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 la. And let's hopefully demonstrate it working. So it's immediately set itself to the set state. When you first switch on a bistable, it's theoretically random as to which one it will actually do. Because this is a simulator, it works slightly differently to the electronics, so it's probably going to do that the same every time I switch it on. Let's potentially demonstrate that by doing the reset and stopping it and then restarting it. Yeah, it's gone so that it's high. So reset turns the queue off, set turns the queue on, and it's got this kind of memory feature, which is going to be incredibly useful. So that's the very first bistable that we've created, and the rest of this series of short series of videos on memory cells is going to build on this in various different ways. So that's it from me for now.